All right, so sequences and series. Let's start with sequences first. All a sequences is a list of numbers. That's all it is. It's just a list of numbers. It's an ordered list, meaning they're in increasing or decreasing order. Each number in a sequence is called a term. So just like when we were doing matrices, each number inside a matrix was called an entry or an element. Here, it's a term. You can have two types of sequences. There is a finite sequence, which contains a finite number of terms, right? So it's a list of 5 terms, 6 terms. You may have like 50 numbers in there. You may have 300 million numbers in there. That's still a finite amount because you can count exactly how many there are. Or you may have an infinite sequence, which is a list that never ends. It's a never-ending list. For example, 2, 4, 6, 8, ... That list of all the even numbers never ends, right? So that's an infinite sequence. A sequence may be able to represented by a function, and you'll see examples of that in this lesson even. Now, when we're talking about matrices, right, each element had the symbol A with a subscript, right? So, for example, it was like A32. Remember? It was A, M, N. Yeah? Here, each term is A subscript N, and N is, basically the nth term. So if you have a list, like here, 1, 3, 5, 7, 9, right? The third number is 5. So you would say A3 is equal to 5. That's it. That just says the third term. Okay? Sometimes we may be able to write an explicit formula which gives the nth term as a function. So for example, rather than, like going step by step, you could say, oh, okay, look, the 54th term is going to be like 3 times blah, blah, blah minus blah, blah, blah. All right. You'll see examples of this as we go on with the lesson. All right. So we're going to start out very, very slow. You've done this back, starting in your pre-algebra days, definitely in geometry, right? Find the next 4 terms. So the first thing you want to do is, find the pattern. All right, so in this one, some people look at a sequence and like this, they can figure out what the pattern is, okay? Some people have to look for it. I was always the ones that had to look for it, okay? There's nothing wrong with that. So what you do is this. You say to yourself, all right, how do you go from the first number to the second number? What do? You subtract 4. Now, how do you go from the second to the third? Subtract 4. Subtract 4. So, okay, that must be the pattern, all right? So then if we want to find the next 4 terms, we just keep subtracting 4. So we get what? And negative 25, okay? All right, the next one here, again, we have to find the pattern. So here we add 3, here, add 5, add 7. So, we're increasing, we're adding consecutive odd numbers, right? So then you add 9 and you get 26, and you add 11 and you get 37, and you get 37, 50, and 65. And that's the next 4. Okay? Here, you're given an explicit formula. Okay? The thing with this is, just by looking at it and just by plugging it in, you can find the first term, the second term, the third term. You could find the 57th term if you wanted to, right? So the first term would be A1. We usually start with n equals 1, not 0. The first term is A1, which is equal to 2. And then A2 would be equal to 9. And A3. And A4. 65. Okay? Now, right. Now, a specific type of sequence is a recursively defined sequence. In these types of sequences, okay, you have a few initial values. You know, maybe like one initial value or 2 or 3 initial values. And after that, each term is a combination of the previous terms, or it uses like the one right before it. Okay, so every time it's like a link, it's like a chain. It goes back and uses the number right before. It goes back and uses the number right before. That's a recursively defined sequence. So for example, look at this one. A1 is 1. That's the first term. And every other term, look, AN is AN minus 1 plus 2. So what does AN minus 1 mean? It's the term right before. Okay? So look, if you have so suppose N is 5, AN is A5, and what's AN minus 1? A4. Right, plus 2. So for example, so now if N is equal to 7, you have A7 and A6. So when you have AN minus 1, that just means previous term. Okay? All right. So look at this one. It says to find the fourth term. Well, the fourth term means you want A4. Well, what is A4? It's 3 times A3 minus 4 plus 2. So basically, if you want A4, you have to use the previous term A3. If you want A9, you have to use the previous term A8, and so on. All right, now we need A3 here, which we don't have. All we have is A1. All right? That means we have to find A3, and then we can use that to find A4. All right, so we have A1. What's A2? A2 is 3 times A1 minus 2 plus 2. So A2 is equal to 9. What about A3? That's 3 times A2 minus 3 plus 2. How much? 26. So now I can find A4. That's 3 times A3 minus 4 plus 2. Okay? All right, so one of the best known recursive functions is the Fibonacci sequence. Anybody seen the Fibonacci sequence? Anybody? Right? Anytime somebody wants to sound smart in the movies, they put in a Fibonacci term in there somewhere. So the Fibonacci sequence is a sequence, it's this. The first few terms are given, so A1 is always 0. A2, that should be a 2, is always 1. And then every other term is the sum of the first two. So if you want AN, you have to add AN minus 1, which is the previous. Okay, and then this is the one right before the previous. Okay? Right. So, find the fourth term of the Fibonacci sequence. All right, so here we have A1, A2. Well, first we need A3, and A3 would be the sum of A2 plus A1, which is equal to 1. So then A4 would be A3 plus A2, which is equal to 1 plus 1, which is equal to 2. So look at how the Fibonacci sequence looks. At first you have 0, then you have 1, then you have 1 again, then you have 2. And each number is the sum of the two numbers that come right before it. So look, this 2 is the sum of these two. So what will be the next one then? 3, and what will be the next one? 5, 8, and so on. Okay? And this pattern is everywhere in nature. In your book, there is an example. It's everywhere, and it's everywhere in nature. So if you plant a new tree, right, you have one branch, which is basically it'll be the stem, or it'll turn into the bark of the tree. So you have one, and then the following month, you have one branch again, and then the following month, you'll get another branch, so you'll have two. Then you'll have like one more, so it'll be three. And then from each of the two last ones, you'll have one more, so you'll have 5 branches. And then the following month, you'll have 8 branches, and then you'll have, it'll be like the Fibonacci sequence. Okay? It's the same with like petals on a flower. If you go outward from the center, if you look at a pine cone, like from the back head on like this, from the bottom head on, the number of like openings is a Fibonacci sequence. And then there is always like the spiral of the shell. There are the perfect rectangles, right? You can divide them into Fibonacci. You start with 1, and then you can divide it into 2, and then divide it into 3, and then 5, and so on. So they're everywhere. Okay. Right. And that's the golden ratio. It's tied to this. Anyways. Okay. So with functions, right? You can get a function, you can have a graph of a function that looks like this. What is the limit of this function as x approaches infinity? Right, it's infinity. Well, what if f of x looks like this? What's the limit of f of x as x approaches infinity? Right, so you know that at infinity, functions can either approach infinity or they can approach a finite number. It's the same thing with sequences. If you get a sequence and if you plot out all of the distinctive terms, okay, those sequences may approach a specific value. In that case, if they approach a specific number, then we say the sequence will converge because it has a limit. Okay? Otherwise, we say the sequence diverges. So if it converges, it is a convergent sequence. If it diverges, it's a divergent sequence. Yes and no. We're going to do these numerically or graphically, whatever you want to call it. So what I want to do is I want to find the first few terms of this sequence. Okay? So A1, right? It's going to be negative 4,000, negative 1 to the 4 to the power of 1. And you know that that's going to be how big? 1,000. Right. A2, it's going to be negative 4,000 times negative 1 over 4 squared. Is that going to be positive or negative? That's going to be a negative what? 250. Because you divide by 16, so it's going to be positive 250. Now, is A3 going to be a positive or a negative number? Positive, right? Because this exponent is going to be odd, so it's going to be negative times negative. It's going to be positive 60.5.
No, it's negative 250. It's negative.
Oh, no, sorry. This is negative, but this is positive. So it'll be positive, negative, positive. And then A4 will be 15. A4 will be negative 15. A5 will be positive 3.9. A6 will be negative 0.97. You have to do at least 5, enough for you to see a pattern. So what we're going to do now is we're going to graph these, and I'm going to change these. I'm going to make this 1,000 and 800, 600, and so on and so forth, okay? All right, so now we graph. So when n equals 1, this is n. When n equals 1, A is 1,000. When n equals 2, we're at negative 250. When n equals 3, we're at 60.5. N equals 4, negative 15. N equals 5, 3.9. N equals 6, right about there. So what's happening? As, it went away. So as n progresses, slowly from both ends, it's beginning to approach 0. This is a convergent graph, so it converges. You do not connect anything because remember, this is just a list of numbers. They're discrete numbers, okay? The next one, I'm not going to go through too much of the math. A1 is negative 2 to the 1 over 2. It's negative 1. A2 is 2. A3 is 4. Negative 4. A4 is 8. A5 is negative 16. This is cool. I like this one. A6 is 32. A7 is negative 64, and then you get to 128, right? So again, I'm going to make this 20, 40, 60, 80, 100. So when n equals 1, we're at negative 1 right there. When n equals 2, we're at 2. And then negative 4. So look, it's jumping again. Positive, then negative. And then positive 8. And then negative 16. Positive 32, all the way up there. And negative 64 here. Do you see what's happening? And then the next one will be up there. And the next one will be further to the bottom and then further to the top. This is diverging. Right. Yeah. For the most part. Okay. All right. This one, obviously you plug this in the calculator. Right? Don't waste too much time doing this. So A1 is 0.1 times 1 over 2 minus 1, 0.1. A2 is 0.0067, and you see here the importance of going into greater number of sig figs, right? A3 is 0.0006, and A4 is even further. Right. This is 4 zeros here. And here, 1, 2, 3, 4 zeros, and then a 57. Okay? So we start at 0.1, and then go further and further down. Okay? So this is clearly doing what? Converging.
Question?
Yeah.
For like a tester quiz.
Big time Calc BC, by the way. Yeah.
For like a tester quiz, would we have to write out like A1 is this, A2 is this, or could we just? Like,
You will have to plot them.
Just see
You're going to have to, I'm going to see,
that it's converging, right?
I'm going to ask you for the plots though.
Do we connect the converging or not?
No, definitely no connecting. These are not continuous functions. Definitely no connecting the points. These are not continuous functions. These are discrete points. Okay? They're just numbers. It's just a list. So there isn't, like, the number between n equals 4 and 5, nothing exists. Okay? In the domain between 4 and 5. You get it? Okay. Now, suppose you took this list, this sequence, and, you know, like you're in a plane, you're going to, I don't know, like Israel, and you've got all this time to kill, and you go, oh my God, I've got this really long sequence here. Let me just sit here and add all the numbers. That becomes a series. Okay? So a series is the indicated sum of all the terms in a sequence. A finite series is the sum of all the terms in a finite sequence, and an infinite series is the sum of all the terms in an infinite sequence. So basically, you have a sequence which is your list, okay? A finite sequence has a finite number of terms, and you just add them, 1 plus 3 plus 5 plus 7 plus 9, and you're done. An infinite series has an infinite number of terms, and you have to add those infinite number of terms. Sometimes, you know, the numbers go to infinity, so when you add all those numbers, you get infinity, but sometimes you don't get infinity, okay? And we'll see some examples here. Now, sometimes you just get sick of adding up all the numbers, so you go, you know what, I'm just going to count to the first 100 and stop. That is called a partial sum. So a partial sum is the sum of the first n terms, and we call it the nth partial sum, denoted by Sn. So if I said, for example, S100, that means you add the first 100 numbers. Okay, and that's the 100th partial sum. How do you find that? Well, you find the first 100 terms, and then you just add them all up. That's it. Okay? All right. Yeah. So here, find the 5th partial sum. So how many numbers do I need? 5. All right. So we're going to have to find the first 5 numbers. This formula will help us generate those numbers. So A1 is -2, A2 1, right? What's A3? 6, A4, and A5, right? So now S5 is what we want, right? Proper notation, and it's just -2 plus 1 plus 6 plus 13 plus 22. $40. Yes.
Let's say 1 plus 6 or 140.
But there are ways to do it.
When is this like applied? Like what? Like everyday thing when you see this?
Your math homework.
That's right, your math homework. The quiz next Wednesday, I think. The test. But we're going to do lots of examples.
What was up with having like 2 tests in a quiz today?
Yeah, oh yeah.
I think it was a mistake.
I feel bad
do
for
not
them.
take this and see if they actually
No, do it in
take
small writing.
No, I feel bad for them. Okay. So
Yeah, let me prompt them.
S4, which means we need the first 4. All right. So I'm going to give you guys 2 minutes. I'm going to pause this 2 minutes to find S4 here. The answer to this one, you get A1 through A4. You add them up. It's 45 over 8, which is 5.625 on the test or on the homework, depending on what you're solving. You may or may not need the fraction or the decimal. All right. So moving on. So all this adding stuff is fine, right? But there is a compact way of writing it, and that is called sigma notation. So just like, you know, we have our alphabet, in the Greek alphabet, the letter that makes the S sound, the S sound, is sigma. And lowercase sigma looks like that. And uppercase sigma is like that. So that's the Greek version of the capital S. Okay?
It's like a half closed infinity. No?
It's
Lowercase is like a half closed infinity.
okay. So now this is the summation symbol, right? Summation. So now rather than saying you want S4, okay, you can say I want the sum of all the terms starting with n equals 1 to n equals 4. Okay? And that's like S4. Now the power really of it, of that notation is, what if you don't want the first four? What if you don't want the sum of the first four? What if you want the sum of, like, the 51st to the 58th? Because those are what are useful to you. So then you would say n equals 51 to n equals, to 58. Okay?
Okay, you just dropped that.
So, it's from the lower to the upper. Okay? It's always from the lower to the upper, never the other way around. And you say n equals or k equals just one time. Okay? And it's, so if we want to write it in, formal notation, your n goes from, it starts at 1, and the place where it ends, that's k. So you start counting n equals 1, n equals 2, n equals 3, n equals 4, n equals 1,000,000, and then n equals k eventually, okay? So that's how that looks, okay? Now, so let's do this one. Again, this is n equals 1 to 4, okay? So what I want to do is, everything else is the same as we were doing before. You want to find a1, which is 1 squared minus 1, which is 0. And then you want to find a2 the same way. You get 2. a3 gives you what? 6. And what does a4 give you? 12. So now the sum of n squared minus n from n equals 1 to 4 is 0 plus 2 plus 6 plus 12, 20. The stuff inside is normally put in parentheses because otherwise it'll be like you have different terms, okay? So for example, if you write this n squared minus n like this, okay, this could be understood that what you really mean is the sum of n squared, and then whatever the sum is, minus n. Do you see that? It's like the associative property. So you have to put parentheses around it if you want the whole thing to be in the sum.
Do we need to write n equals 1, or can we just write 1?
No, you do n equals, because you want the name of the counter. No, on the top you definitely don't. Okay. These are it's a special case, and you'll learn to recognize this as a pattern. So this one, look, it's saying to add all the ones from n equals 1 to infinity. So you're going to have an infinite number of terms. Okay? So here's what you do. It's all about patterns. So here's what we're going to do. Let's see what A1 is. A1 is 3 times 1 over 10, right? Which is like 3 over 10. Now, A2 is 3 times 1 over 10 squared, which is like 3 over 100. A3 is 3 over 1,000. A4, 10,000. So you already see a pattern emerging, right? The next one is going to be 3 over 100,000, 3 over 1,000,000, and so on and so forth. Hang on. Now, we're going to add all of this, okay? So if we're going to add it, it's going to be 3 over 10 plus 3 over 100, 3 over 1,000, 3 over 10,000, plus dot, dot, dot. Now, in decimal, this is 0.3 plus 0.03 plus 0.003, 0.0003. And when you add all of those, right, like decimal values, you get 0.3333 with a bar, which is what? It's 1/3. So this is an example. So this is an example that's counterintuitive. Because you think just because you're adding an infinite number of terms, your answer is going to be like infinity. But no, it's a finite convergent series. Okay? It's a finite number. So the sequence, There is one like this for anyone, 1/9, 1/8,
Wait,
all of the repeating numbers.
but it would be really complicated because it has to be like 0.6 plus
You'll see on the homework, and then on the quiz, and then on the test.
Okay, so you think for like these, we should do like the first 3 numbers, and then by then we'll have it or something?
You should, yeah, you should do enough
But see it.
that you can see a pattern. Okay? Now, here's one where you have to write in sigma notation. Okay? So it says the lower bound is given. That means this is the number, that you start from. So, when you do this, you're going to start with n equals 1. Now, the way you do this is this. Each one of these, right, you number them. So this is entry number 1. So this is the term when n equals 1, n equals 2, n equals 3, n equals 4, 5, 6, 7, 8. So first of all, you're going from n equals 1 to n equals 8. So here you have 8. Okay? Now, what you have to do is not like before, where you were looking for a pattern between consecutive terms. You have to find the pattern that relates the value of n to the entry itself. So the value of n to the entry itself. The value of n to the entry itself. So how are 1 and negative 2 related? How are 2 and negative 1 related? How are 4 and 1 related? What do? You subtract 3. So for each of them, okay. We want a pattern that relates the value of n. So here n equals 1 to this number negative 2. N equals 2 to this number negative 1. So you ask yourself, if I have a number 1, what can I do to it so it's negative 2? If I have a 2, what can I do to it so it's negative 1? If I have a 5, what can I do to it so I get 2? Right? So what do you do each time? You subtract 3. So whatever your value of n is, you subtract 3. So in here, that's what you have to write. It's n minus 3. So in the first problem that we solved in this lesson, we were looking for an operation that got us, linearly each progressive term. How do we go from 2 to 3 to 4 to 5? Right? You add 5, but you add 1, but that's not what we're doing here. In this case, you want to relate upwards. Okay? And sometimes it's going to be as simple as n minus 3. Sometimes it's going to be n squared plus 1. N squared over 2 minus 2. Okay? You have to think outside the box. Sometimes they get pretty interesting. Okay? They get pretty involved.